Problem number 23. Steve determines the spring constant K of a spring by applying a force F to it and measuring the change in the length dx. The tools he uses to measure F and dx both have a constant absolute uncertainty, leading to an uncertainty in K of delta Ks. If Tiffany measures the same spring constant with the same tools, but by using a force that is 5 times larger, what will her uncertainty in K be in terms of delta Ks? Solution for problem number 23. First, let's write hook law for this spring. We have force F equal spring constant K multiplied by dx, change in length. From here, K equal F over dx. And we can count in that case what is the relative uncertainty for measurement of K is this one for Steve. For Tiffany, we have another formula. We have force 5 times greater. It means that enlargement will be 5 times greater for this spring, but absolute uncertainty is the same. It means that from here we can find that delta K for Tiffany equal to 0.2 delta K for Steve. And this is the answer C, and that was solution for problem number 23. Problem number 24. A mass M is connected to one end of a zero length spring with a spring constant K. The other end of the spring is connected to a frictionless bearing mounted around a horizontal pole so that the mass can swing in a vertical cycle of radius r around the pole. The setup is shown in the figure below. What is the vertical distance h between the center of the circular orbit and the axis of the pole? Assume that both the diameter of the pole and the rest length of the spring are neglectable compared to r. Solution for problem number 24. This problem could be solved using a vector form. Let's write equation for total force acting on our mass. So total force equal negative K multiplied by vector L minus mg multiplied by unit vector J in the vertical direction. Here vector L, that's vector from pole to our mass. We can represent vector L as a vector H, which is from pole to the center of rotation, plus vector R from center of rotation to our mass. And now we have this equation, and for point below the pole H to be center of rotation, we have to equalize second and third member to each other. KH equal mg and h equal mg over k, which is answer D, and that was solution for problem number 24. Problem number 25. A ball of a neglectable radius and mass m is connected to two ideal springs. Each spring has a rest length L0. The springs are connected to the ball inside a box of height 2L0, and the ball is allowed to come to equilibrium, as shown. Under what condition is this equilibrium point stable with respect to small horizontal displacements? Solution for problem number 25. First, let's find the position for equilibrium, which is below initial position in the middle of the box. We have minus K1z minus K2z equal mg, where z is a vertical displacement for equilibrium. From here we can find z. That will be negative mg over K1 plus K2. Now let's find what is the force created by upper string and lower string. Upper string will create pulling force and lower string will create pushing force. For upper string we have F1 equal K1z, which is K1 mg over K1 plus K2, and for lower string we have F2 equal K2z, which is K2 mg over K1 plus K2. Now let's do small horizontal displacement x. In this case, because change of length of this strings has a second order of smallest compared to x, we can count only part of horizontal change in force. For upper string we have x over L0 minus z multiplied by force F1, and for x2 we have x over L0 plus z multiplied by F2. Condition for stable equilibrium will be F1x plus F2x less than 0. It means that after putting all this expression to this inequality, we have this inequality. And now let's do counting. After some multiplications and manipulations, we have this inequality, and finally we have K1 minus K2 greater than mg over L0, which is answer C, and that was a solution for problem number 25.